Hello, my name is Sand-STA and I'm a field application scientist for PerkinElmer covering the materials characterization product lines. Today this talk will focus on how thermal and elemental analysis can be used in the mining industry. Here's a brief outline of what we will cover today. It will include both the thermal and elemental portfolio overview of what PerkinElmer offers. We will then cover some applications including proximate analysis of coal and coke, loss on ignition for solid combustion residues, mineral and clay analysis with DSE and TGA, and then we'll cover some hyphenated techniques for evolved gas analysis. Finally, we'll cover the ultimate analysis of elemental analysis, which will cover CHN of coal and oil shale samples. So to start, here are the offerings for thermal analysis. You can see that there's 4 different options here. The first one being differential scanning calorimetry, then thermal gravimetric analysis, TGA, dynamic mechanical analysis, DMA, and then thermal mechanical analysis, TMA. The thermal analysis group of techniques measures physical and chemical properties as a function of temperature and time. This table here provides the properties measured by each technique. In the first column, we have DSE, and DSE is used for phase transitions like melting points, crystallization, glass transitions, heat of fusion, specific heats, and cure times. The next column over is the TGA, which is used for things like percent moisture or decomposition, percent ash, and actually you can get some composition analysis out of it. DMA is used for modulus or viscosity studies, along with tan delta or dampening, stress strain studies, glass transition, creep and recovery, and then other shrinkage forces. And then finally, the TMA is used for thermal expansion and compression forces. Mostly today, we'll be talking about the DSE and the TGA. Here are PerkinElmer's offerings for thermal analysis. You can see that we have quite a bit of instrumentation that covers this kind of analysis. We provide 4 DSE models, 2 TGA models, 2 simultaneous TGA-DSE models, 1 DMA, and 1 TMA. The DSE 4000 and 6000 are single furnace heat flux DSE models. This is what you will see on the market with all the other competitors that are out there. The DSE 8000 8500 are dual furnace power compensating DSEs, and PerkinElmer has a patent on this technology, so we are the only ones that can do that. TGA 4000 is a top loading TGA balance with a 1 microgram sensitivity, whereas the TGA 8000 is a research grade 0.1 microgram bottom loading TGA, so you get much more sensitivity using that kind of instrument. All above models have auto samplers, and the main difference between the STA and the STA 8000 is the maximum temperature. Now, what are you getting with an STA? The STA is a combination of a TGA with a DSE or DTA signal. So you'll get both information like you would get with a TGA and DSE all out of one instrument. And then finally, we have our DMA 8000, which has a fluid bath for immersion test and controlled relative humidity accessory, and the TMA, which has a temperature range of -80 to 800 degrees, just to give you a little information about each. So now that we've covered the instrumentation that PerkinElmer offers and what you can get out of thermal analysis in terms of data, let's talk a little bit about the different applications in mining that you can use these instrumentations for. The first example is the use of an STA, so that's a DSE or a TGA and a DSE signal for approximate analysis of coal and coke samples. If you look at the curve here on the left, you'll see 3 different curves. The green curve is the percent weight loss of coal heated with 2-step temperature program, which is depicted in the blue curve. The first weight loss at 100 degrees is due to moisture, followed by the loss of organic volatiles as the sample is heated to 950 degrees C. The purge gas is then changed from an inert nitrogen gas to air at around 47 minutes, and this is to oxidize and remove any carbon so then we can do ash analysis. The DSC thermogram in red provides additional information that confirms the aforementioned transitions and reactions. The graph on the right-hand side is the approximate analysis of metallurgic coke. As an ASTM method is used to measure the percent weight of volatiles, fixed carbon, and ash in inorganic components. So here you can see two examples of how this is used for coal and coke. Another example application would be the loss on ignition test, or LOI, and it's a standard method for determining the carbon content of fly ash for coal-fired boilers. An ASTM method D7348 describes two ways of testing solid combustible materials with a macro TGA, or essentially a muffle furnace. Either a single-step or two-step procedure can be adapted. The problem with this standard method has been long revealed because the weight loss can be from other reactions such as dehydration of calcium hydroxide or decarbonation of calcium carbonate, in addition to the loss of carbon. So this table here summarizes those errors in the LOI test of various coals. The weight loss due to dehydration carbonate calcination is shown to be comparable to even higher than the loss of unburned carbon. Therefore, the loss on ignition results can bear significant errors. More details of this study can be found in the reference given at the bottom. Solutions to combat these errors include using a TGA, which will allow you to apply a temperature program to separate out weight loss, or using a hyphenated technique, such as a TGA mass spec. There's also elemental analysis, which is your ultimate analysis, which will give you carbon, hydrogen, and sulfur information. Here you can see an example of using those solutions for the loss on ignition test of fly ash. Using a hyphenated technique like TG mass spec will allow for identification of the cause of weight loss and should be used as a complementary technique to the standard loss on ignition test. So this graph here is a little hard to distinguish with the colors, but let me just point out real quickly what you're seeing. This line in black here is your TGA curve, and so you can see that it has the shape of weight loss like you were seeing before. And then laid on top of that are the mass specs you were seeing for water, CO, and CO2. And the results are sensitive to these different kinds of parameters such as sample size, heating rate, types of gas, and your gas flow. But it's used to complement your standard LOI test. Here's a long list of ASTM and ISO methods that are using TGA as the primary technique for the analysis of coal and coke materials. You can go back and reference these methods later. Another common DSC application is the determination of solid phase transitions in ceramic materials. This helps the formulation and optimization of production conditions of the specialty ceramics. So if you look at the graph here on the left, the bottom curve shows the tetragonal to monoclinic transition of zirconia ceramics with different selenium oxide doping levels where the material is heated. Increasing this oxide level significantly reduces the transition temperatures and the enthalpy or peak area as well. The cooling curve on the top shows the reverse transitions with the same exact trends. And so if you look, you're seeing separate curves for each doping level and how that changes the peak area of those curves. If you want to look at porcelain clay with an STA, which is simultaneous TGA and DSC signal, here you can see it used as a test of dry porcelain clay. The DSC curve in red demonstrates the dehydroxylation around 574 degrees C and the unique spinel crystallization around 1000 degrees C. Other exothermic events visible above 1200 degrees C in Figure 2 correspond to the formation of molinite and crystallolites of interest to the ceramic industry. The TGA curve in blue confirms the initial endothermic weight loss process is due to the dehydroxylation of the kaolinite to form metakaolinite. In the STA, quantifying this transformation allows determination of the kaolinite, the primary component in the porcelain clay formation. This is done by comparing to a similar analysis of commercially refined kaolinite. The porcelain clay yields a weight loss of 6.4, while that of commercial grade kaolinite has an average dehydroxylation weight loss of 12.7%, if you're looking at the weight loss curve in blue. From the two weight loss calculations, we determined that the percent commercial grade kaolinite in the clay formation here is 50.5%. Alternatively, we can make a determination from comparing the STA dehydroxylation heat flow peak, so that's the area of the data, from the ratio of the DSC peak areas of the kaolinite. Analysis yields 51.9%. So you can see how close those two numbers are by using the two different sets of data. Another use of thermal analysis in clays is shown here. The TGA on the left helps find the time needed for completion of calcination at certain temperatures. So you'll see each curve is held constantly at a certain temperature and monitored over time. You'll get out the residual mass information. The DSC on the right shows temperature ranges where dehydration, dehydroxylation, and recrystallization occurs during this heating process. And so you can use both different techniques to get different information out from the sample. Another application for thermal analysis is here. For clear glass and for translucent ceramic porcelain pieces, one would expect that a primary component would be amorphous material where crystallites are not scattering incident light. This is what makes it clear. This graph shows two STA heat flow curves for the first and second heat of a cone 10 glaze sample. On the second heat, after the sample has been heated to 1300 degrees C roughly, corresponding to the cone 10 to set the glaze, or allowing the components of the glaze to react and produce the amorphous phase desired for the ceramic finish, the second heat, that will be the one in blue, you will see an event which is a glass transition. This is the softening point of the vitreous components that is indicated by the increase in specific heat or an endothermic shift in the heat flow curve. So you'll see a decrease in that baseline as the post-fired material is reheated in the STA. This is truly a glass transition and softening point, and it was confirmed by running the samples in a thermal mechanical analysis penetration mode. So that's the TMA that we offer. Similarly, TGA is often used to analyze natural porous materials such as zeolites. The dehydration or loss of water and dehydroxylation are easily detected and quantified, and you can see that here in this graph. DSC is also used to analyze mineral materials. This calcined diatomaceous earth sample shows its signature phase transition around 190 degrees C on both the heating and cooling curves. So you can see this by placing a baseline across the line and seeing the peak height of the peak in the curve. So switching gears to talk about cement from our other materials, the specific heat, Cp, which is the amount of heat per unit of mass required to raise the temperature by 1 degree Celsius of cement, needs to be measured in material characterization of modern construction materials. In this example, specific heat of two major cement ingredients, corundum and tricalcium silicate are measured in a wide temperature range using an ASTM method, seen here at the bottom of the screen. You can reference this method to find out more about this information. And then lastly, we have the next couple of slides on a study of prehydration of cement and its mitigation. Ordinary Portland cement, OPC, prehydrates during storage and handling in most environments, forming hydration products on or near its particle surface. Prehydration is known to reduce OPC reactivity. To develop a better understanding of prehydration, by intentionally exposing an OPC powder to either water vapor or liquid water, we can investigate the extent of which premature contact of OPC with water and other potential reactants in liquids and or vapor state can induce different surface modifications on the OPC grains, and therefore its ability to do its job. The influence of prehydration on the rates of reaction as measured using isothermal calorimetry for A, the graph A on the left, is your heat flow, B, cumulative heat release, and C, cumulative heat release at 1 day, 3 days, 7 days, and 28 days for all cement paste mixtures normalized by the heat released by the as received paste mixture. So, prehydration due to exposure to moisture does reduce the reactivity of OPC as seen in all three graphs. If we go a little bit further into this and start looking at OPCs with TGA as a function of the prehydration index, you'll see in A, you'll see the degree of reaction, B is the compressive strength, development of plain OPC paste as a function of specimen age, and C is the normalization compressive strength of plain OPC paste as a function of the prehydration index. This work shows that the degree of reaction and compressive strength of OPC paste can be quantified as a function of the prehydration index. It gains insight into both the factors controlling OPC prehydration and the likely mechanisms which fine limestone can offset the detrimental effects of prehydration. So now let's switch gears from applications to what you can get out of using hyphenated techniques. We've already kind of discussed a few hyphenated techniques, but let me go into this a little bit further. Coupling or hyphenating two or more analytical instruments can give us the advantage to detect and separate chemical aspects of interest with higher sensitivity and selectivity. It can uncover results and insight not possible with just using an individual technique like DSC or TGA. Hyphenation falls into three major categories. The first one involves the modification of sample environment. For example, adding a UV source to DSC or DMA for testing materials under UV radiation, or curing, coupling with a humidity generator or fluid bath for the DMA to control humidity or immersion tests in that kind of condition. The second type is simultaneous analysis. The sample can be measured by two techniques at the same exact time. An example of this is the TGA DSC, aka an STA, short for simultaneous thermal analyzer. We've talked quite a bit about this throughout this talk, using the STA to be able to get both DSC and TGA signals at the same time. The last category, evolved gas analysis, is the combination of a TGA or an STA with a gas phase analyzing tool such as FTIR or GC mass spec, so that the emitted gas or evolved gas coming from a TGA sample can be examined further. So let me show you what one hyphenated technique that PerkinElmer offers looks like. Here in the picture you can see a TGA hyphenated to an FTIR, which is then hyphenated to a GC mass spec. You'll also notice that there's transfer lines. These transfer lines are heated to ensure that the gas stays in the gaseous phase as it transfers from one instrument to the next. You'll essentially be using the TGA or the STA for weight loss analysis, and then the FTIR and the GC mass spec will be used on the evolved gases to be able to analyze what is coming off. These transfer lines are connected through a control module and vacuum pump for stable temperature and to allow the carrier gas flow rate control. The choice for FTIR for Frontier or Spectrum 2 models with both zero gravity gas cells allows real time of gas analysis. Followed by the GC, the Claris GC or the SQ8 mass spec are the GC mass spec options offered by PerkinElmer. PerkinElmer is the only one out there that can offer a full suite hyphenated solution under one single provider. If you go elsewhere, you would have to couple two companies in order to work together to be able to make this kind of instrument hyphenation. So now that we know what it looks like, let's do some comparisons of why you would want to pick one hyphenation technique over another. So here we've laid out the TGIR, so that's thermal gravimetric analysis and infrared spectroscopy, TG mass spec, and then TG-GC mass spec. And you can see that there's pros and cons for each one of them. And it's important to know which one will be better for what you need to do. Now I'm not going to read through these, but this will give you an idea of which is the better suited for your application. So now that we've talked about hyphenation, let's go through a little bit of data before we move on to elemental analysis, the ultimate analysis. So here's the analysis of sedimentary quartz sand, and here's it with the STA. When you hyphenate an STA to an IR, you can get even further data from it. So in terms of just the STA data that's coming out, you're going to get DSC and TGA data. The DSC data shows a characteristic silica inversion peak at 573 degrees C, which corresponds to the crystal lattice change in heating from triagonal alpha form to the hexagonal beta form. So that's in the blue. And then you'll have your TGA, which captures the volatile losses, which is then identified in the FTIR. So these volatiles will then be transferred through that transfer line into the FTIR. So you can see a decrease in weight loss as you increase your temperature. So here's your FTIR results that come off of that STA run. The FTIR spectra are collected continuously over the entire heating process in real time. And it's clearly seen that CO2, CO, and water emit from the sample as the sample is being heated. And so water is going to be over here and a little bit in this region. Your CO2 is here, and then your CO is in this region also. Here are 4 FTIR spectras to show you how the FTIR changes at different temperatures. It allows you to take a closer look at the spectrum change as a key of weight loss steps. And so you can see at each different temperature, the spectra looks slightly different, especially if we monitor this 3000 region here. And so 3000 is where your CH stretching falls. And you can see how that changes over temperature, which will give you information about the products that are coming off during that heating. So here are gas evolving as a function of temperature graphs. And so you can see if we separate it into each functional group, carbon, hydrogen, CO2, CO, and water, you can see that over the temperature range, how the absorption of those appear when they come into the spectra and where they are saturated as they come off of that scan. You can see that water comes off way earlier which is what you would expect. You would expect it to start coming off around 100 degrees and then hit a mass. And then you'll see that CO2, CO, and CH3 come in a little bit later. And then finally, the last technique we want to talk about is our EA2400 elemental analyzer. It uses the Dumas method to measure 5 elements: carbon, hydrogen, nitrogen, sulfur, and oxygen. Samples are combusted in an oven at 1000 degrees C, where the elements are converted to simple gases like CO2, water, nitrogen gas, SO2, and CO. And then they're separated by a GC column and measured by a thermal conductivity detector for the calculation of percent of each element. ASTM D5357 is a standard method for using such a technique for coal analysis. ASTM D3176 and ASTM D5373 methods describe the standard procedures for using the ultimate analysis for coal and coke. You can reference these methods on your own. ASTM Committee D5 has specified methods of homogenizing and pulverizing coal samples prior to analysis. This will be important to get a reproducible data set out. But here you can see a table that shows accuracy of percent carbon, percent hydrogen, and percent nitrogen of some typical coal samples determined using the EA2400. Details about this study can be found in the listed application note below. Fly ash samples can be analyzed using organic elemental analysis. Because of the lower carbon content, much larger sample weights can be than coal and coke can be used here. Total carbon is measured here on the left-hand side, and that's labeled as TC. Inorganic carbon from carbonates can then be removed with an acid to allow the measurement of unburned carbon and as an alternative approach to a loss on ignition test. For coal and coke samples, the hydrogen and carbon H to C mole ratios can be used as an indicator of heat values when comparing coals. The lower the H to C ratio, the higher the energy content. This is due to higher carbon content increasing the energy value. And so you can see this kind of analysis on the right-hand side in that table with varying of different coal materials. And lastly, we have the EA2400 is used for oil shale industry to monitor the production, where oil is removed by heat in the retort. The percent carbon and hydrogen and sometimes the percent sulfur need to be compared before and after the oil extraction. And so you can see down in the table on the right, raw oil shale, the percent carbon, hydrogen, nitrogen, and sulfur, and then after the oil extraction and how those compare to each other. So that completes my talk on thermal analysis for mining materials. I appreciate you spending the time to listen, and we will take any questions. Thank you.